In this video, I'd like to tell you a bit about the math behind large margin classification. This video is optional, so please feel free to skip it, but it may also give you better intuition about how the optimization problem of the support vector machine, how that leads to large margin classifiers. In order to get started, let me first remind you of a couple properties of what vector inner products look like. Let's say I have two vectors u and v that look like this, so both two-dimensional vectors. Then let's see what u transpose v looks like. And u transpose v is also called the inner product between the vectors u and v. U is a two-dimensional vector, so I can plot it on this figure. So let's say that's the vector u. And what I mean by that is if on the horizontal axis, that value takes whatever value u1 is, and on the vertical axis, the height of that is whatever u2 is, the second component of the vector u. Now, one quantity that would be nice to have is the norm of the vector u. So these are double bars on the left and right that denotes the norm or the length of u. So this just means really the Euclidean length of the vector u, and this by Pythagoras theorem is just equal to u1 squared plus u2 squared root, right? And this is the length of the vector u. That's a real number. So it says, what is the length of this? What is the length of this vector down here? The length of what is the length of this arrow that I just drew? Is the norm u. Now let's go back and look at the vector v, because we want to compute the inner product. So v will be some other vector with some value v1, v2,
in this case, the number of positive examples is much smaller than the number of negative examples because y equals 1 so rarely. This is what we call
now,
the case of
let's go back and look at how to compute the inner product between u and v. Here's how you can do it. We're going to take the vector v and project it down onto the vector u. So I'm going to take a orthogonal projection, or a 90-degree projection.
So the problem
project
with
it down
using
onto
classification
u
error or classification
and what I'm going to
as
do
our
is
evaluation
measure the length of this red
Let's say
line
you
that I
have
just
one
drew
learning
here. So I
algorithm
call the
that's
length of that
getting
red line p.
99.2%
So p
accuracy.
is the length or is the magnitude of the projection of the vector
Let's say
v
you make a
onto
change
the
to your
vector u.
algorithm and you
So
now
let me just write that down. So p is the length
accuracy.
of the projection
That is 0.5%
of the vector v
So
onto
is this an improvement
vector
to the
u.
algorithm or not? One of the nice
And
things
it's
about
possible to
having
show
a
that
single row number
the inner
evaluation
product u
metric is this helps
transpose
us
v,
to quickly
that this
decide
is
if
going
we
to be
just
equal
made
to
a big
p
change to the algorithm or not.
times the
By going
norm
from
or the length of
99.2%
the vector
accuracy
u.
to 99.5% accuracy.
So this is one way to compute the inner product, and if you actually do the geometry and figure out what p is and figure out what the norm of u is, this should give you the same answer as the other way of computing the inner product, right? Which is if you take u transpose v, then u transpose is this u1, u2 is a 1 by 2 matrix, and then times v, and so this should actually give you u1 v1 plus u2 v2. And it's sort of a theorem of linear algebra that these two formulas give you the same answer. And by the way, u transpose v is also equal to v transpose u. So if you were to do the same process in reverse, instead of projecting v onto u, you could project u onto v, then do the same process but with the rows of u and v reversed, and you should actually get the same number, whatever that number is. And just to clarify what's going on in this equation, the norm of u is a real number, and p is also a real number, and so u transpose v is the same regular multiplication of two real numbers of the length of p times the norm of p. Just one last detail, which is if you look at the norm of p, p is actually signed somewhere, and it can be either positive or negative. So let me say what I mean by that. If u is a vector that looks like this, and if v is a vector that looks like this, so if the angle between u and v is greater than 90 degrees, then if I project v onto u, what I'll get is a projection that looks like this.
Example where the actual clause is 1 and the
that
predicted
length
clause
P,
is 1.
and in this case, I will still have that U transpose V is equal to P times the norm of U, except that in this example, P will be negative. So, in inner products, if the angle between U and V is less than 90 degrees, then P is the positive length of that red line. Whereas if the angle, this angle here, is greater than 90 degrees, then P here will be negative of the length of this little line, of that little line segment over there. And so the inner product between two vectors can also be negative if the angle between them is greater than 90 degrees. So that's how vector inner products work. We're going to use these properties of vector inner product to try to understand the support vector machine optimization objective a little better. Here's the optimization objective for the support vector machine that we worked out earlier. Just for the purpose of this slide, I'm going to make one simplification, just to make the objective easy to analyze. And what I'm going to do is ignore the intercept terms. I'm just ignore theta 0 and set that to equal to 0.
And what that says is,
to make things easy to plot, I'm also going to set n, the number of features, to be equal to 2. So we have only 2 features, x1 and x2. Now let's look at the objective function, the optimization objective of the SVM. When we have only 2 features, when n is equal to 2, this can be written 1/2 of theta 1 squared plus theta 2 squared, because we only have 2 parameters, theta 1 and theta 2. And what I'm going to do is rewrite this a bit. I'm going to write this as 1/2 of theta 1 squared plus theta 2 squared, and then square root squared. And the reason I can do that is because for any number, w, right, the square roots of w and then squared, that's just equal to w. So you took square roots and squared, and it should give me the same thing. And what you may notice is that this term inside the parentheses, that's equal to the norm or the length of the vector theta. And what I mean by that is that if we write out the vector theta like this, as theta 1, theta 2, then this term that just underlined in red, that's exactly the length or the norm of the vector theta, following the definition of the norm of the vector that we had in the previous slide. And in fact, this is actually equal to the length of the vector theta, whether we write it as theta 0, theta 1, theta 2, that is if theta 0 is equal to 0, as I assume here, or just the length of theta 1, theta 2. But for this line, I'm going to ignore theta 0, so let me just treat theta as this, let me just write theta, the norm of theta, as this theta 1, theta 2 only. But the math works out either way, whether we include theta 0 here or not, so it's not going to matter for the rest of our derivation. And so finally, this means that my optimization objective is equal to 1/2 of the norm of theta squared. So all the support vector machine is doing in the optimization objective is minimizing the squared norm, the squared length of the parameter vector theta. Now what I'd like to do is look at these terms, theta transpose x, and understand better what they're doing. So given the parameter vector theta and given an example x, what is this equal to? And on the previous slide, we figured out what U transpose V looks like for different vectors U and V. And so we're going to take those definitions, with theta and xi playing the roles of U and V, and let's see what that picture looks like. So let's say I look at just a single training example. Let's say I have a positive example that drawing as a cross there, and let's say that's my example xi. Right. So what that really means is that I've plotted on the horizontal axis some value xi1, and on the vertical axis xi2. That's how I plot my training examples. And although we haven't been really thinking of this as a vector, what this really is, this is a vector from the origin, from 0, 0, out to the location of this training example. And now let's say we have a parameter vector theta, and I'm going to plot that as a vector as well. And what I mean by that is I'm going to plot theta 1 here, and
not possible
theta
for
2
an
there.
algorithm to sort of quote cheat and somehow
So
get
what is the
very
inner
high
product,
precision and
theta
regularity
transpose
by
xi?
doing some simple
Well,
things.
using our earlier method,
Zero all
the way we
time,
compute
always
that
doing
is
y
we
equals 1 all the time.
take
And so,
my
we're
example
much
and
more
project
sure
it
that,
onto my
plus
parameter
five
vector
with
theta,
high precision, high
and then I'm going to look at the
actually
length
makes
of this
and this gives
segment
us
I'm
a
coloring in
useful
red,
evaluation metric
and I'm going to call that
actually
P
understand whether,
superscript
our
I
algorithm may be doing
to
well.
denote that this is a projection
So
of
one
the ith
final
training
note, the
example
definition
onto the
of precision in
parameter
recall.
vector
The
theta.
way we define precision
And
in
so what we
recall,
have
usually
is that
we
theta
use the
transpose
convention
xi
that y
is equal
one
to,
in the presence
following
of
what we
a
had on the
rare
previous
cause.
slide, this
So
is going to
if
be
we're trying
equal
detect
to
some rare condition,
P
such as cancer, hopefully that's a rare
times
condition.
the
Precision
length
recall
of the
defined
norm of the
setting
vector
y
theta.
equals 1,
And this is of
rather than
course
y
also
equals 0,
equal to
to be sort of the
theta
presence
1
of a rare
x1
cause that we're trying
plus
to
theta
detect.
2 x2.
And,
So
by
each of
using
these
precision and
is an
recall,
equally valid
what
way of
what
computing the
happens
inner
is that
product
even if
between
we have very
theta
few
and
classes,
xi.
it's not
Okay,
possible
so where does this
for
leave
us
us?
to
What this means is that
cheat
these
and
constraints,
like
that theta
one all the
transpose
time,
xi be
like
greater than
zero
equal
all
to
the
1,
time,
or there's less than
even
equal to
high
minus
precision
1.
recall.
What this means is
And
it can
so
replace
if
these with
high
constraints
precision,
that
high precision, high
pi
then we're actually
times
confident
x be
that,
greater than or
the
equal to
algorithm
1,
has to
because
be
theta
equal,
transpose
even
xi
if we have very
is
few
equal to
classes.
pi
So,
times the
for
norm of
policy
theta.
classes, precision
So
recall,
writing that
we
into our
use
optimization
direct
objective, this is what we get,
calculate
where I
what
have,
it's doing,
instead of
and this
theta
optimal
transpose
metric
xi, I now have
for
this
learning
pi
methods,
times the norm
then,
of theta.
looking at classification
And just to remind you, we worked out earlier too that this optimization objective that
in
can
the
be
previous
written as
video,
1
I
half
talked about
times
error
the norm of
analysis
theta
and the
squared.
importance of having
So,
error metrics. That is,
now let's
having
consider
a
the
single
training
row
example
number
that we
evaluation
have at the
metric
bottom.
for your
And
learning
for now,
algorithm
continuing to
tell
use the
how well it's
simplification that
In
theta
the
0 is equal to
context of
0,
evaluation
let's see what
and
decision
error
boundary
metrics,
the support
there's
vector
one
machine will
important
choose.
case
Here's
where
one
it's
option.
particularly tricky
Let's say the
to
support
come up
vector
with
machine
an
were to
appropriate
choose
error metric or
this
evaluation
decision
metric
boundary.
for your learning
This is not a very
algorithm.
good choice
That
because it has
case
very
is the
small
case
margin.
of
This
what's called
decision boundary
excused
comes very
classes.
close to the training
Let me tell
examples.
you what that means.
Let's see why the support vector machine will not
Consider
do
the
this.
problem of cancer
For this
classification.
choice of
where we have
parameters,
features
it's
of
possible to
medical
show
patients
that
and we want to
the
decide whether or not
parameter
we have
vector
cancer.
theta
So this is like
is
the
actually at
malignant
90 degrees
versus
to the
benign
decision boundary.
tumor
And so
classification
that green
example
decision
that we had
boundary
earlier.
corresponds to
So
a
let's say
parameter
y
vector
equals 1 if the
theta
patient is
that points in
cancer,
that
and y equals
direction.
0 if
And
it's
by the
tumor.
way, the simplification
We
that
might train
theta
a
0
logistic
equals
regression
0, that just
classifier,
means that the
and
decision
let's say
boundary
we
has to
test
pass
our
through the
classifier
origin
on a
0,
test set
0 over
and
there.
find that we get 1%
So now let's
so
look
we
at
get
what this implies for the
99% correct
optimization
accuracy.
objective.
Seems like a really impressive result.
Let's say that this example
Correct
here,
99%
let's say that's my first
but now,
example,
let's say we find out that only
x1.
0.5%
If we look at the projection of this
of
example
training
onto my
test
parameters
actually
theta,
have cancer.
that's the
So
projection.
only half
And
a
so
percent of
that little line
patients
red
that come
segment,
through our screening
that is
process
equal
have
to
cancer.
P1.
In this
That's going to be
case,
pretty small.
The 1% error
Right.
no longer looks so
And
aggressive.
similarly,
In particular,
if
here's a piece of code.
this
Here's actually a piece of
example
non-learning
here, if
code
this happens to be
that,
x2,
takes us
that's my
input
second
features
example,
X, and it ignores
then
it.
if I
It
look
just
at the
says
projection
y
of this
equals 0,
example
and
onto
always
theta,
predicts, nobody has cancer.
then
And
let me
this
draw this one in
algorithm
magenta.
would actually get
This little magenta line
0.5%
segment,
error.
that's going to be
So this is even
P2.
better
That's the
than
projection of the
1%
second
error that we
example
did just
onto
now.
my
This is a
onto the
non-linear
direction
algorithm.
of my
This is
parameter
predicting
vector
y
theta,
equals
which
0
goes like
all the
this.
time.
And so
So
this
the
little
setting of where
projection line
the
segment is going to be
ratio
small.
of
P2
positive
will
to
actually be a negative number.
examples is
So
very
P2 will be
close
because
to
it's
one
in
of
the
the two extremes,
opposite
where
direction.
in this
So
case,
this
the number
vector
of positive
has
examples
greater than
is
90
much,
degree
much
angle
smaller
with my
than the
parameter
number of
vector
negative
theta, it's going to be
examples,
less than
because
0.
y equals 1.
And
So
so what we're finding
this
is that these
what we call
terms
the case of
Pi
classes.
and are going to be pretty
We just
small
have a lot more
numbers.
examples
And so
of
if we
one
look at the
class.
optimization objective and see,
And
well,
by
for
just
positive
predicting
examples,
y
we
equals
need
0 all the time,
Pi
or maybe I predict
times
y
the
equals
norm
1
of
all the time,
theta
an algorithm
to be bigger than or equal to 1.
well.
But
So the
if
problem with using
Pi over here,
classification
if
error
P1
or
over
classification
here
accuracy
is pretty
as
small,
our
that means
evaluation
that we
metric is
need the
following.
norm of theta
Let's say you have one learning algorithm
to be
that's
pretty
getting
large, right? Because if
99.2%
P1 of theta is
accuracy.
small, and we want
So that's
P1,
what,
you know,
0.8%
times the norm of
error.
theta to be bigger than or equal to 1,
Let's say
well,
you
the only
want
way
to
for that to be
change your
true, for the
algorithm
product of these two numbers to be large if P1 is small, as we said, normal theta to be large. And similarly, for our negative example, we need P2 times the norm of theta
to the algorithm or not. One of the nice things about having
to be less than or equal to minus 1, and we saw in this example, right, that P2 is going to be a pretty small negative number, and so the only way for that to happen as well is for the norm of theta to be large.
Did we just do something useful, or did we just
what we're doing in the optimization objective is we're trying to find a setting of parameters where the norm of theta is small, and so so this doesn't seem like such a good direction for the parameter vector theta. In contrast, let's look at a different decision boundary. Here, let's say this SVM chooses that decision boundary. Now the picture is going to be very different. If that's the decision boundary, here's the corresponding direction for theta. So with the decision boundary being that vertical line, that corresponds to, it's possible to show using linear algebra that the way to get that green decision boundary is to have the vector theta be at 90 degrees to it. And now, if you look at the projection of your data onto the vector x, let's say as before that this example is my example x1. So when I project this onto x, onto theta, what I find is that this is P1, that length there is P1, and from other example, if that example is x2, and I do the same projection, then what I find is that this length here is P2, really this will be less than 0. And you notice that now P1, right, and P2, these lengths of the projections are going to be much bigger. And so if we still need to enforce these constraints that P1 of the norm of theta is greater than 1, because P1 is so much bigger now, the norm of theta can be smaller. And so what this means is that by choosing the decision boundary shown on the right instead of on the left, the SVM can make the norm of the parameters theta much smaller. So we can make the norm of theta smaller and therefore make the squared norm of theta smaller, which is why the SVM would choose this hypothesis on the right instead. And this is how the SVM gives rise to this large margin classification effect. Namely, if you look at this green line, if you look at this green hypothesis, we want the projections of my positive and negative examples onto theta to be large, and the only way for that to hold true is if, surrounding this green line, there's this large margin, there's this large gap that separates the positive and negative examples. And there's really the magnitude of this gap, the magnitude of this margin is exactly the values of P1, P2, P3, and so on. And so it's by making the margin large, or by making these terms P1, P2, P3, and so on, that the SVM can end up with a smaller value for the norm of theta, which is what it's trying to do in the objective. And this is why the support vector machine ends up with a large margin classifiers, because it's trying to maximize the norm of these p-i's, which is the distance from the training examples to your decision boundary. Finally, we did this whole derivation using this simplification that the parameter theta 0 must be equal to 0. The effect of that, as I mentioned briefly, is that if theta 0 is equal to 0, what that means is that we're entertaining only decision boundaries that pass through the origin, so decision boundaries that pass through the origin like that. If you allow theta 0 to be non-zero, then what that means is that you entertain decision boundaries that do not pass through the origin, like that one that I just drew. And I'm not going to do the full derivation, but it turns out that the same large margin proof works pretty much in exactly the same way. And there's a generalization of this argument that we just went through, and I'm not going to go through, that shows that even when theta 0 is non-zero, what the SVM is trying to do when you have this optimization objective, which again corresponds to the case of when C is very large. But it's possible to show that even when theta 0 is not equal to 0, the support vector machine is still finding, is really trying to find a large margin separator between the positive and negative examples.
that actually have cancer.
So that explains how the support vector machine is a large margin classifier. In the next video, we'll start to talk about how to take some of these SVM ideas and start to apply them to building complex nonlinear classifiers as well.